A vector basis consists of vectors, not necessarily perpendicular, that fully describe a space. In statics, to fully describe a two-dimensional space, you will need two vectors. And to fully describe a three-dimensional space, you'll need three vectors. Typically, in statics, we choose to describe three-dimensional and two-dimensional space with right-handed orthogonal unit bases. In this two-dimensional space, the z-axis is coming out of the plane described by the right-hand rule. When solving a problem in statics, bases are not always given. In fact, it is up to you to choose your base to describe the problem at hand. With practice, you will become good at choosing convenient bases that will greatly simplify your problem. The orientation between orthogonal unit bases A and B can be described by using a powerful tool called a rotation matrix. Since this is in 3 dimensions, and actually all problems will use a 3x3 matrix, where the elements of the rotation matrix rotating the unit bases A to the unit bases B, where I is the row and J is the column of the matrix, can be described as AI dotted with BJ. This is equal to the cosine of the angle between the two unit vectors as described by the dot product. Here I have worked out the matrix rotating A to B. Note that the first row, so the I1 and J1 is described by AX and BX. So AX dotted with BX. The 1-2 entry is AX dotted with BY. Using this format, you can generate a 3x3 matrix that will be your rotation matrix to describe the rotation of the bases from A to the bases B. This will be very useful for complicated three-dimensional problems that are described by more than one basis. What if you're given the rotation matrix to rotate the bases A to B? How would you rotate from B to A? That information can be stored inverting the rotation matrix from A to B. Inverting the 3x3 matrix can be a difficult task. However, when inverting a rotation matrix for orthogonal bases is simply the transpose of the 3x3 matrix. Now, I don't expect you to have taken linear algebra and know how to invert a 3x3 matrix, but know that a transpose of a 3x3 matrix is a much simpler operation to form. And how will we do that? So the rotation from B to A is equal to rotation matrix from A to B transpose. To transpose a matrix, you would take the first row and put that in the first column of the transpose matrix. Take the second row and put it in the second column, and the third row into the third column. In this example, we'll generate a rotation matrix for two bases whose AX and AY and BX and BY axes are in the same plane or coplanar. This is a common situation when you have a 2D problem. Note that the BZ and the AZ axes are collinear or equivalent, and BX has been rotated from AX by some angle theta. Using geometry or SOHCAHTOA, we can see that BX can be described in the AX bases as the cosine of theta AX plus the sine of theta AY. BY can be described as minus sine of theta AX plus cosine of theta AY, and BZ is equivalent to AZ. To put that into a rotation matrix, to rotate from B to A, so BX can be described by the cosine of AX plus the sine of AY plus 0 AZ. So we have cosine theta sine theta, and we fill in 0 for bx.az. For by, it can be described by the minus sine of ax and plus the cosine of theta ay. And again, 0 az. bz can be described by simply az. So 0, 0, and since they're equivalent, we have a 1. This will describe the rotation from the bases b to the bases a. Recall that the rotation from a to b is simply the r from b to a transposed. To see how a rotation matrix can help us in a 2D problem, let's revisit the cart. Recall that earlier I had said that if we use two bases, we could describe our owed VCM as ax plus L over 2 nx. And I had said that this was equivalent to the solution we had found earlier as a plus L over 2 cosine theta x plus L over 2 sine of theta y hat. Now, how do we make a rotation matrix between these two bases? To do that, we'll put their origins together, and since they are coplanar, their z-axis will be pointing in the same direction. Now with the bases stacked on top of each other, we can easily fill out the rotation matrix. Note that nx can be described as the cosine of theta x hat plus the sine of theta y hat, and 0 in the z direction. And ny can be described as the minus sine of theta x hat plus the cosine of theta y hat, and 0 in the z. And nz and z hat are going in the same direction, so 0, 0, 1. Now looking back to our vector described by two bases, we see that nx is equal to the cosine of theta x hat plus the sine of theta y hat. Plugging in, we have r from O to BCM is equal to a x hat plus cosine of theta x hat plus sine theta y hat, which is equivalent to the position vector we had found before, describing it in only one basis.